Welcome. This course shows practical implementation in Python, starting from a clean virtual environment. Install the core stack with pip, LangGraph, LangChain OpenAI, Pydantic, and Pydantic.env. Put keys such as OpenAI API key in a .env file and load them with load.env so secrets stay out of code. Map the architecture to code. Planner, executor, and memory become concrete Python modules. Python is preferred because of its AI ecosystem, data parsing strength, and native tool execution. A clean layout often includes state.py, tools.py, nodes.py, and graph.py. Initialize the client with Chat OpenAI, for example GPT-4o, at temperature 0 for reliable behavior. Use typing tools such as typedict and annotated so state contracts stay explicit and robust. Section 1 takeaways: isolate the environment, secure keys with .env, and use type hints for reliable state passing. Pause here. Start with environment and secrets before building agent logic. Now the quick check. Quick check after Section 1. Which practice best keeps API keys out of source code? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 2 defines agent state in Python with typedict schemas and Pydantic models. State is central because one shared object acts as the single source of truth passed between nodes. Declare class agent state as a typed dict so each state key is explicit. Annotate messages with add messages so chat history accumulates instead of being overwritten. Add steps and max steps fields so the runtime can track execution limits. Use Pydantic models such as plan output to guarantee structured LLM responses. Prefer returning key value update dictionaries so the runtime merges changes cleanly into main state. Test initialization with a clean dict, such as empty messages and steps set to 0. Section 2 takeaways. Typedict defines state, reducers append history, and Pydantic enforces output types. Pause here. State contracts come first, and reducers protect history. Now the quick check. Quick check after Section 2. Which Python class is commonly used to define explicit state schema keys in LangGraph? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 3 covers tool binding, turning Python functions into LLM callable tools. The @tool decorator wraps a plain function, such as calculate tax of amount, into an LLM tool. Docstrings matter because the model reads them to decide when and how to call a tool. Bind tools with LLM.bindTools, passing functions such as calculate tax and web search. When tools run code, Isolate execution in a sandbox so unsafe code cannot harm the host. Wrap tool calls in try-except blocks so failures become readable feedback instead of crashing the graph. For independent requests, asyncio.gather can run multiple tool calls in parallel. Package tools as a list, such as search tool and database tool, then pass that list into agent nodes. Section 3 takeaways. Decorators expose tools, docstrings guide selection, and try-except improves resilience. Pause here. Tools are functions, and docs steer the model. Now the quick check. Quick check after Section 3. Why are docstrings critical when defining tools? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 4 shows how to write node functions that process state and return updates. A node is a function, like reasoning node, that takes agent state and returns a dictionary of updates. Inside the reasoning node, invoke LLM with tools on the current messages and capture the response. Return a delta such as messages with the response and steps incremented by 1. The action node reads tool calls from the last message and matches them to tool names. A pre-built tool node can iterate tool calls and dispatch the matching Python functions. A pre-built tool node can iterate tool calls and dispatch the matching Python functions. An evaluator node checks whether the response satisfies final conditions or needs another retry. Store node functions in nodes.py so the codebase stays modular and easy to maintain. Section 4 takeaways. Nodes are functions on state. They invoke the LLM with tools, and they return deltas. Pause here. Nodes stay small and return deltas. Now the quick check. Quick check after Section 4. What must a node function return in a state graph framework? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. Section 5 assembles the graph engine: nodes, edges, routers, and compilation. Instantiate workflow as state graph of agent state to lock the state schema. Register nodes with add node, mapping names such as agent to reasoning node. Set the entry point with an edge from start to the agent node. Define a router such as should continue that returns tools or end, then attach conditional edges. Add a return edge from tools back to agent so observations re-enter reasoning. Pass recursion limit in the invoke config, for example 10, to kill infinite loops. Compile with workflow.compile to turn the definition into a runnable engine you can also visualize. Section 5 takeaways. State graph wires nodes. Conditional edges control looping, and compile builds the app. Pause here.
Graphs make control explicit, and routers decide continue or stop. Now the quick check.
Quick check after Section 5. What parameter prevents an infinite execution loop? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown.
Section 6 covers running, streaming, debugging, and production packaging in Python. Invoke the graph with app.invoke and an input such as calculate tax to get the final output. Use app.stream to render live node output events while the agent runs. Track cost by printing response metadata token usage for prompt and completion tokens. Enable Langsmith tracing with LangChain tracing v2 set to true. Then inspect latency and tokens per node. Pause before tools by compiling with a checkpointer and interrupt before set to tools. Resume by updating state if needed and calling app.invoke with none and the same config. In production, catch recursion errors cleanly and wrap the agent in a fast API backend with async endpoints. Section 6 Takeaways. Invoke or stream live output. Enable tracing for debugging, and use checkpointers for human approval. Pause here. Streaming reveals the loop, and tracing explains the cost. Now, the final section check. Quick check after Section 6. How do you pause graph execution before a tool runs for human approval? Choose A, B, C, or D. Take 1 minute to think, then choose A, B, C, or D. The correct answer is not shown. You completed a quick check after every section. You can now implement Python agent graphs with clear state, tools, and control. Congratulations! You completed practical implementation in Python. Thanks for watching.